It's okay. So it's okay. I'll start without pointer. I don't think I need it. So my name is Oswaldo Dieguez. Since a year and a half ago, I'm in the Department of Material Science and Engineering here at Tel Aviv University. I'll be chairing this session, and I'm also the first speaker. So, and I'm late. So I'm going to talk about what we do in my group, which is atomistic simulation of materials. I'll start by saying a few words, very general words about it. Then I'll present some materials that are of interest to us, which are multifunctional oxides, in particular ferroelectrics and multiferroics. I'll illustrate the kind of work we do by presenting our latest work. And then I'll briefly, given the nature of this workshop, I briefly summarize other projects we are doing or we want to do. So what we do is we simulate materials by starting with a very simple assumption, which is that they are made of atoms. Once we decide materials are made of atoms, we need a model for the interaction between these atoms, and in the group, we work with different kind of models. The simplest model you can imagine is that they are hard spheres, that they don't interact other than by colliding. If you have 4 of them, you already need a computer to solve the Newton equations. So we have computers that do that, and they look a bit more modern than this. But even this kind of very simple model, which was kind of the first time that molecular dynamics were done, can allow you to get insight into properties of materials. In this case, from that very simple model, you can see that there are liquid to solid transitions in systems, yes, even if the atoms don't attract each other. So it all depends on what you want to know about your material for which method you are going to use. Nowadays, the most used methods are so-called first principles methods, in which the atom is not a sphere, it's not a ball, but it's made of charges, the nuclei and the electrons. The electrons obey the usual, there are many ways to proceed from here, but in the most typical methods, the electrons obey Schrödinger's equation, which we cannot solve exactly, but we can solve approximations to it, again, using computers. And from this, we can get things like, with very good accuracy, we can get the bond lengths, energy formations, magnetic moments of magnetic atoms, band structures, in our case, the polarization of ferroelectrics, etc. As I said, there are many kind of methods you can use. This is a graphic made of already a couple of years ago, in which I counted how many papers were published that contain these kind of methods in their text. So you have a trade-off between the accuracy you want for your calculation and how much detail you can have in your material, how many atoms you put in the material. If you need to simulate the virus of tobacco, and this has been done, and you want to put all the million atoms there, your only option is this kind of option. Maybe these days we are getting here, but you have pair potentials, which is the simplest way, in which you just, the atoms are balls again, and they interact with a force or energy that depends on the distance, angles, etc. You can add electrons to your methods. So you have electrons, but still you treat them in a very simple way. Or you can add electrons, and you begin to treat them in a more quantum mechanical way. But in this case, you still make an important approximation, which is that the electrons see an average of the rest of the electrons. If you want to remove this approximation and take into account correlation between electrons, then you have to go to quantum chemistry methods or GW methods or quantum mechanics methods. This graph is to illustrate that, thank you, that many in the community think that the best trade-off is given by density functional theory. So density functional theory allows you to get a relatively good accuracy, but and still you can deal with systems that have hundreds of atoms in your unit cell. So in our case, the material, the first study I'm going to present is about some materials we are interested in, which are oxides, in particular perovskite oxides. It is known that by changing the composition of layers in this kind of materials, you can change very substantially the properties of the material. You can get them to be polar if they are not. You can change their piezoelectric properties, etc. This kind of material, and here is an experimental image, high-resolution TEM, of this kind of interface between materials that shows that we have a lot of regularity in them. They can be growth epitaxially and coherently, and this is the perfect kind of system to study with our methods. Because in our methods, we always will have a unit cell that contains the atoms, and we repeat the unit cell infinite times to create a periodic solid. The more perfect the solid is, the smaller the unit cell will need. If we have defects in the solid, then we need to replicate these defects. The defects cannot be very close because otherwise they have a spurious interaction between them. It costs us more. But in this kind of system, we can manage quite well with the kind of methods we have. So in our case, we want to know the dielectric properties, piezoelectric properties, ferroelectric properties, and in many cases, the magnetic properties of the materials, of these perovskites. Getting even more particular with talking about multifunctional oxides, the kind we are interested in this work is what is called multiferroics. Multiferroics show, and in particular magnetoelectric multiferroics, which show both electric ordering or electrical ordering, so polarization, and magnetic ordering. Maybe some of you are more used to magnetism, so in magnetic materials, if you apply a magnetic field, you get a magnetization. In ferromagnets, if you remove the magnetic field, you still get the magnetization. So in many computer memories, how you store information is by switching between 1 and 0 orientation of the magnetization. You can do the same with polarization. Some materials, like the molecule, if you think of the molecule of water and you put many of these together, you get a polarization per unit volume, and you can switch in some materials, which are the ferroelectrics, you can switch that polarization in two opposite directions in the material with the presence of an electric field. So the idea of multiferroics, or magnetoelectric multiferroics, is that if you have a material that has both polarization and magnetization, you can try to switch the polarization with a magnetic field or the magnetization with the electric field, because there will be a coupling between the magnetic and electric properties. So the revival of this field, although it was active in the 70s, the revival of this field came in 2003 after this paper was published, in which a material called Bismuth Ferrite showed that it had a very large polarization, like no other material. Actually, it has other of the typical ferroelectrics we have, like lead titanate or barium titanate, have less polarization than bismuth ferrite, and it also had a magnetic moment. It turned out that that magnetic moment that was described here was not as high as thought, and in reality, in bulk bismuth ferrite, you don't really have a net magnetic moment. But this kind of investigation prompted other researchers to try to find materials that are multiferroic. So in particular also, the coupling, the electromagnetic coupling in bismuth ferrite is not good. So in our case, we've done work in bismuth ferrite trying to find other phases and not the ground state that has these properties we are looking for. And that's part of the work the group has done. Some other part of the work, and this is done in collaboration with Jorge Dieguez at Barcelona, where I was before, is to try to find other materials. In this case, we looked at other transition metal oxides with bismuth. If you go to the experimental literature and you look at the ones that from the same row that can be grown as perovskites, the bismuth scandiate is an insulator, so it might have a polarization, but in this case it doesn't, and it's a diamagnet. With chromium, you have another insulator that is also paraelectric, so there is no polarization, so it's not going to be ferroelectric. The same is true for bismuth manganate, but in the case of bismuth manganate, this is the only robust insulating ferromagnet among the transition metal oxides. Bismuth ferrite is the one I mentioned before. Bismuth cobaltite is known to be ferroelectric, but is not ferromagnetic. It's antiferromagnetic and has a net moment of 0. And bismuth, I mean, this is another interesting material for other reasons, but it's a metal, and it's not going to be ferroelectric. In this work, we looked at bismuth manganate. So bismuth manganate is an insulator, as I said, with a large magnetic moment per manganese atom of around the nominal moment 4, but it's centrosymmetric, so it's paraelectric. The structure is like in all this perovskite oxide, it's a distortion of the perfect cubic perovskite. So we get an octahedra of oxygens, and inside it there is manganese, and in the corners around the octahedra there is bismuth. There is a very particular distortion in this material that is not often seen, because this material shows one other particularity, which is that it has orbital ordering. One of the DZ2 orbitals, it's oriented differently in the two inequivalent manganese ions, and this is what causes the ferromagnetism to appear. If you go to the good enough Kanamori rules, you can see that in this kind of situation, you can get a net positive ferromagnetic alignment. So this is what the bulk of this material looks like. We want, ideally, to keep the ferromagnetism and to develop polarization. So first principles calculations were done before we did this, but they didn't find any transition in the material. If you begin to try to, for example, grow it as a film, and you begin to change the strain of the film, nothing happens. The phase is the same until at some point the magnetic moment disappears. The magnetism disappears. However, we had some experience looking for different phases of bismuth ferrite, so we thought we could do a more extensive or systematic search for phases of this bismuth manganite. So what we did is we chose phases of bismuth ferrite that we knew were stable, so we knew they were at least saddle points of the energy surface. We substituted iron into manganese, and we optimized them. To optimize them, we use one of the first principles codes, in this case VASP, with some methodology to treat the inner electrons, and we optimize all possible pseudocubic 40-atom unit cells that we found. In density functional theory, I didn't say anything about it, but in density functional theory, you always make one approximation regarding what is called the exchange and correlation potential. So it's known that the energy is a function of the electron density, but it's not known which functional, the energy is a functional of the electron density, but it's not known what the expression of the functional is, so you need an approximation. Many times you use what is called the local density approximation or the generalized gradient approximation, and it works. One kind of materials where it's known that it does not work is materials with transition metal atoms like these ones, where the electrons are highly localized. The typical density functional theory implementations fail to localize these electrons because of the way they are constructed. So in many cases, what should be a robust insulator like this with a 2eV gap comes out as a metal. There are several ways to address this kind of materials. One that is very much used is to add what is called a Hubbard U. So you put a penalty in your energy, that favors localization of these electrons. In this case, the d electrons of manganese. Usually, when the typical approximation doesn't work, this one works. But in this case, and in other cases with manganese, which is a D4 configuration ion, it does not work in the sense that it's not able to open a gap that is large enough to make an insulator out of the material. And also, one of the typical test calculations you have to do is to make sure your ground state phase, which is what I showed before with the magnetic ordering, is still the ground state. So in your computation comes out as the lowest energy phase. In this case, it doesn't. There is another phase, which is very typical also in perovskites, which is non-polar, which is centrosymmetric and has a PNMA. For those of you that know a bit more of perovskites structure, this is very common and for some reason comes as the most stable one. This in the experience I have with perovskites, it never happened, in the sense that one of the DFT functionals plus U always gives you very good distances, very good energy difference, well, not so good energy difference, but very good distances, and certainly gives you who is the ground state. Not in this case. So when this happens, and we know that is because it is not able to open the gap, there is further improvements that you can do to your methodology, which usually come with a pay-you-pay in computer time simulation. So another way you can proceed is to use density functional theory, and in this exchange correlation potential I said, you can put part of it that comes from Hartree-Fock, from the exact exchange potential of Hartree-Fock. Like this, you construct these so-called hybrid functionals, but then you have to do density functional theory and Hartree-Fock. This kind of calculation takes 100 times more than this kind of calculation in the computer. So what takes 1 hour here, it takes us 3 days here, each of these points. So, but it gives us the right ground state. If we look at the bond distances in the ground state, which is the one we can compare with experiment, we get them with accuracy better than 1%, and we get the ground state to be the ground state. So in the rest of the work, we used this hybrid functional, and we optimized all these phases. And for each phase, we optimized with any of these possible typical magnetic ordering. So the ferromagnetic phase, and then a phase in which the neighboring manganese have opposite spins, and then one in which in plane have this opposite spins, but out of plane parallel, and another one that is the opposite. So the bottom line is we get the ground state to be the ground state, and then we get a non-polar, so no ferromagnetic, and also not magnetic, not ferromagnetic and not paraelectric phase, and then we get something that looks like the ground state of bismuth ferrite, and then we get these phases that are particular perovskite phases in the sense that it's not really a perovskite anymore if you impose that a perovskite must have an octahedra. The octahedra move up so much that they break this bond, so what you have is pyramids. This has been seen before in one material, which is bismuth ferrite. So if you grow bismuth ferrite as a film and you grow it at a substrate that has a small enough lattice constant, you get this kind of phase, which is ferroelectric. So in our case, we want this to be the phase of bismuth manganite. How do we do that? Well, precisely as I said, you can grow it as a film. So in the computer, again, we simulate what is the energy of the film in the ground state. So you can take the ground state, distort it a little bit, and grow it as a film and compute there. You can do it with the super tetragonal phases, and you can do it with the phase that is like the one of bismuth ferrite, and indeed you get that they are ferroelectrics. So the prediction of our study is that paraelectric bismuth ferrite should be a ferroelectric if you grow it at this kind of lattice constant or this kind of lattice constant. There are substrates to do that in both regimes. So if you grow it in yttrium aluminate or in PCT, which is somewhere here, you should be able to get this. Now, in principle, if you compute the strain, this is a 6 or 7% strain, you should be worried that the material is not going to accept this. It will break by having dislocations or some kind of defect. But the important point, and this is the same reason why it happens in bismuth ferrite, is that those phases, as I showed in the previous transparency, are already minima in the bulk. They just are minima of higher energy. So if you take the system to a point that is close to that phase, it will stay stable. And this is what happens with bismuth ferrite and what we think it should happen with bismuth manganate. So you should have another ferroelectric with a very large polarization and maybe maybe ferromagnetism. I say maybe because we did calculations. We can also do calculations for regarding the ferromagnetism, and we computed the differences between different magnetic arrangements. So the 4 magnetic arrangements that I said for the super-tetragonal and the rhombohedral phase, we compute the difference between them. The one that is the most stable is one of the antiferromagnetic ones, but the ferromagnetic one is very close. Now, as an illustration of other kind of things we can do with computational methods, I have to say all this is done at 0 temperature, like all calculations at DFT by default. For this kind of perovskites, this should be okay, since it's known that bismuth ferrite or bismuth manganite, they keep the same structure up to, like bismuth ferrite, up to 1,000 Kelvin. So not much happens there. We expect this to be the same. But if you want to compute things like the Néel transition temperature, so the temperature at which the material becomes paraelectric instead of antiferromagnetic, you need to average over configurations. You are not going to be able to run enough configurations with this method. What we do is we fit the results from DFT or DFT-Pratt hybrids to simpler models that allow us to do many calculations for many configurations, and this way using statistical mechanics to compute when the transition occurs. So we have a very simple model, Heisenberg model, in which the energy of the different configurations just depends on the alignment of the spins. We fit the exchange constants to the DFT calculation, and the lines you see there is the lines given by this model. So we only use 2 exchange constants, the ones of atoms nearest neighbors in plane or out of plane. The rest, we cut the interactions, and still we get quite good fit. And then, because it's very cheap to compute this, we can compute things like the Néel temperature, and we get, as expected, a small Néel temperature of around 100 K, which is the experimentally known Néel temperature for the ground state. So for the other states we found, we expect a similar temperature. So this is work, again, as I said, done with Jorge, and that we just submitted for publication. Other things the group is doing, just to give a very brief review, is this is a collaboration with experimentalists at the Weizmann, in which they find an electromechanical effect in a material, but that is not a piezoelectric. So it's not a first-order electromechanical effect. It's second order, but it's very large. They don't understand exactly why. So we are able to look at the atomic structure, and so far we have reproduced exactly the displacements of the atom in the material that are particular, and we will be able to try other substitutions. This is a material that has impurities, so we want to know for other impurities whether the effect is still there, whether it's better, whether it's worse, and what can we understand from our simulations. We also do some development of codes, in particular when I was in Barcelona, I collaborated with what is called the Siesta. It's one of these codes you use to do this calculation. So we do development of this kind of tool if we need it. For example, now we are applying for this is one of the directions in which the field is the field of computational materials is moving. We are applying for a project to be able to join Siesta with other kind of faster methods of the type I mentioned at the beginning, so that, for example, if you are interested in ferroelectrics like us and you want to study the effects like domain walls, you can apply the quantum mechanical treatment exactly at the domain wall, but far from the domain wall, you still need atoms because the atoms are there, but you can treat them with other methods. Another direction the field is going is this high throughput discovery, in which you automatize your programs to, instead of looking at the experimental materials that are known, you combine elements from the periodic table and you try to do many calculations so that you get out of 10,000 trials 3 or 4 materials that have particular properties that might be interesting. So in the field of perovskite oxides, we have some lines to try to do this in mixed perovskites, and that's it for me. Thank you. Questions? Yes.
Could you comment on the Bismuth Ferrite system? You said that it's anti-ferromagnetic there?
Bismuth.
What went wrong?
I don't know. I think maybe too many oxygen vacancies is one of the things I've heard. Something spurious in the experiments they did. Nobody has. They got a magnetic moment of 1 Bohr magneton per ion, iron ion. Nobody has ever found that high moment. Then they found, it's a complicated system where the spins are canted, and also there is a spiral on the spin that is very long range. This is in the bulk. If you grow it as a film, you are able to kill the spiral, and you get a very small magnetic moment of 0.1 or even less. But nobody has ever reported again that 1 Bohr magnet.
Is that the science paper? My understanding is there's an impurity iron paper.
There was a name.
Yeah.
What about this program, Quantum Espresso, this Italian fellow at MIT? I think he's at EPFL now.
So Quantum Espresso is another code like VASP. It has the advantage of respect to VASP that is free. Anyone can download it. It has the disadvantage that it doesn't implement everything that VASP implements. So there are some things we want, and in Quantum Espresso they are not there. But they keep developing, and for many materials it's as good alternative as the other codes.
Is it as good as VASP?
Depending on for a very large set of materials, both will give you exactly the same answer. Then there is a lot of theories that are implemented in one and not in the other. Depending on what you want, you are obliged to choose one. But for typical calculations, they are the same. Yes?
You had an interesting proposition, the way that there was a global minimum for a non-ferroid phase, and then there was these local minima on either side. Do you know, has anyone ever, your proposal was that if you create sufficient strain, it'll actually stay there.
Yes.
Because locally, has anyone ever experimentally had a material that formed like that?
Yes, in the case of bismuth ferrite, this is what happens. Experimentally, it was first found that there was this super tetragonal phase. We then, Jorge and I and others, found that this phase, but it was not understood very well why the strain was so large, and you still would get this, because in other things like lead titanate or barium titanate, if you compress it more than 2%, the material will create dislocations. This one is 6-7%, and it doesn't. But it's because there is the phase there already. Yes?
Just about that, it's not a local minima. Just as a comment, epitaxially stabilized, and they exist as long as the substrate exists. Without a substrate, they have only one minima. It's not local minima, it's independent stable minima under different thermodynamic conditions. I'm just curious about the bismuth manganate. I'm not in this field at all. What's the current status from your talk about theory versus experiment? So if I understood correctly, the bulk material without epitaxial stabilization, DFT does not give the right crystal structure, but HSC does. And then when you get the right ground state by HSC, is it in agreement with experiment that it is
very good.
orbitally ordered?
Yes, we checked that it's orbitally ordered, and we checked bond distance. It's very good.
And so for the equilibrium one, it's not magnetic though, according to HSC?
No, it is. The ground state is magnetic. We get,
But the ground state is not ferroelectric.
but the ground state is not ferroelectric.
Now, if you now change the subject and put a substrate and make a different material by in-plane strain, then you pay about 100 millivolts per atom destabilization. And at that point, it is also ferroelectric.
Yes, but not ferromagnetic.
But not magnetic. Now, are those statements in agreement or disagreement with experiment? Or
So in experiment, the bulk is known to be magnetic and to display orbital ordering, and in theory, this is what we get. So
is it ferroelectric?
no, and in experiment is paraelectric, and in theory is paraelectric. It's the same thing. For the films, there is no.
For the epitaxial strain.
Yeah, for the epitaxial strain. But why do you say not for the film? This is what I try.
The attribute, in my opinion, is not the word film. The word is
Okay.
the in-plane lattice constant is artificial
Okay,
change.
it's true.
That's
We,
epitaxial constant.
yes, there is a step. We need to reason still that if you put it as a film,
The substrate, it goes back to the original state. It's only on a substrate that you have.
yes, yes,
So it's a different material because it includes
Yes.
the substrate.
yes. So in this case, there are films growth at that epitaxial lattice constant. So there are a couple of papers in the literature, and they don't say much, other than we find a very large polarization, but it's not clear why, and we don't. So we think it's because they are seeing this phase.
But even though the energy is enormously higher than the ground state, if I saw about 100 millivolts per atom, still you think that experimentally they can stabilize something.
Yes, because it's very far. So, and the energy difference is very similar to the one that occurs in bismuth ferrite. And in bismuth ferrite, this phase exists. I mean, it has been characterized by many groups. And the curves look similar.
100 millivolt.
Yes, but the thing, it is 100 millivolt. But when you are in this regime, the one that is the ground state is way above. So what will the material do? I mean, if it was barium titanate,
Effective phase. This phase
yes,
down the energy stabilized because of the
I understand. I'm saying that with bismuth ferrite, the image is very similar, and the phase is that one. It's very well characterized. Okay.
I have a question about the compound with scandium, and it's just curiosity. With a colleague of mine at Northwestern, David Dunan, we've been working for about 15 years on aluminum scandium alloys because you form an Al3, it's an L12 structure, aluminum-3 scandium, and it has a very high melting point, so you can produce high-temperature alloys of aluminum with it, but it's very expensive scandium. So we dope it with rare earth, even number rare earth elements that are less expensive than scandium, and they substitute on the scandium sublattice, and it's really useful, the alloy, except that scandium is expensive. So I'm wondering, this phase that contains scandium, what are its unique properties?
So, okay, I think we can talk about it later because I took a long time. But what is known is that it's paraelectric so far. It could be made probably also ferroelectric, and in this kind of material, if you substitute, you probably will get very good magnetic properties. But this is I'm conjecturing. So maybe we can.
No, because the more uses for something that contain more uses of materials that contain scandium, the lower will be the price.
Okay. Okay, I can tell you what I know later. But I think that's it for me.